Right, so I think we can reconvene. Our last speaker for the morning session is going to be Siming He.
I would like to thank the organizer for inviting me here. And today I'm going to talk about chemotaxis-fluid systems. Basically, it's an application of this mixing and enhanced dissipation mechanism we learned so far. And now along the way, I'll try to use a concrete example to reveal what's been done up to now. So I'll divide the talk in 4 parts. First, I'm going to introduce the problem that I'm going to address, which is called a coupled chemotaxis-fluid systems. And I'm going to elaborate a little bit on this enhanced dissipation business that Christian emphasized today. And now, lastly, I'm going to talk a little bit about how do we actually use this kind of mechanism to address problems in our real life or applications. So let's get started. So the first topic, this is our object. We are talking about chemotaxis. So basically you have some petri dish, and now you put chemicals on the petri dish, and now the cells here will aggregate towards the chemicals. So towards the center. And now basically this is a nonlinear aggregation effect, and now that will create the cells to be aggregates, and now create a blow up. And now along the boundary, and now you can see the bacteria also do random Brownian motions. Okay, biologists think that, okay, the cells do a run and tumble behavior. So first it runs in the direction of the chemical gradient, and now it tumbles and now moves in some other direction. So there's 2 competing forces here. One is aggregation caused by chemicals. The other is random Brownian motion. So the balance of these 2 forces will create interesting phenomena. Okay, so we are going to talk about this model, which is called the Pala-Keller-Segal equations. And now, first, I'm going to give you some literature review on some classical Pala-Keller-Segal equations. So the equation looks like this. So as I explained, there are 2 competing phenomena in this model. So first of all, and now once you have a chemical bacteria densities, it will secrete chemicals. So it will create a chemical gradient. So all the density will aggregate towards the higher concentration of chemicals. So basically this term creates a blow up in the equation. And now the bacteria also do random Brownian motion. So we have diffusion here. Okay, so that's the 2 main players in this game. And now there are certain rules in this equation. So the first rule is that the total cell population is preserved, because you can do integration on both sides. And then basically, thanks to the divergence structure of the equation, the total cell population will be preserved. And now there's another rule. It's like there's actually dissipative free energy in this equation. So basically for physicists, they like dissipative energies. And now here we have a decaying quantity. So once you have a decaying quantity, basically you have more understanding of the system. Okay, so basically when we are trying to cook up new system, we should somehow respect this kind of rules. Okay, so that's the basic quantities in this equation. And now I'm going to review a little bit about literatures here. So basically, if you have a bacteria here, and now it will secrete some chemicals, and now basically the chemical gradient will point to the center here, and now basically it will attract all the bacteria to come closer. And now at the end of the day, if you have a lot of cells in this petri dish, and now you'll form finite time singularities. Okay, so that's the overall, that's the long-term behavior of this system. So basically, if you don't have enough cell, okay, if the total mass is less than A pi, and now your solution will be globally regular. So everything will be smooth. It behaves like a modified heat equation. And now if the total population is exactly equals to A pi, and now you are going to form Dirac mass as time goes to infinity. And now if you have more than A pi mass, and now you can do a simple virial identity argument, and now by computing the variance of this cell density, okay? And now you just do some symmetrization trick and then use some relation satisfied by the chemical gradient. And now you are going to end up with a constant, okay? So M here is like the L1 norm of your solution, and now that's preserved in time. And now if your M is bigger than A pi, you can see that this number is a negative number. So the variance will go to 0 in finite time. But then on the other hand, you also know that the L1 norm is preserved. So basically you create a Dirac in finite time. But then of course, this is just a contradiction argument. And now basically tells you, okay, the solution cannot continue. So just like this picture, okay? So that's what happened in 2 dimensions, okay? Now, let me give you another key property of this equation. That is, in 1 dimension, this equation is globally regular. You can easily do all sorts of energy estimate you like, and now it will be very nice, okay? And now this is the key observation for our latter applications, okay? So then this is a simulation in 2 dimensions. Basically, you expect if there are too many cells and then they aggregate, and now you have formed Dirac singularities. Okay. Now that's the basic setup. And now, first of all, okay, I'm trying to introduce our model. So we are not working with classical Keller-Siegel equation. We try to take into account fluid interactions. Okay. So first of all, basically, we have the cell densities, and now you have some fluid advection, and now you have some classical aggregation and diffusion. And now I will not say too much about the chemical equation at this point, because there are many modeling aspects here. And now the fluid equation satisfies the Navier-Stokes equation with forcing. Okay, so the literature on this topic is vast. Okay, I'm not going to saturate all of them here. But then basically, one of the modeling thing is like, okay, now you basically throw all your cells in the water, okay? And now you expect that, okay, the cells are just staying there. They are not going to the bottom. So basically, you have some buoyancy force acting from the bacteria density to the fluid. And now basically you have a N0 minus Ng term. Okay, you can add it to the fluid equation. And now you try to look at the long-time dynamics. And now basically there are no good results. There are not too many sharp results here. Basically, people can do small data, global well-posedness, etc. But then nothing too much known is about the long-time behavior. Okay, so first of all, I'm going to talk a little bit about our model. So basically, I'm trying to simplify the model by just saying that, okay, my chemical are secreted by the densities, and now everything will reach equilibrium in a very fast time scale. So basically solves the elliptic type equation. And now we introduce this very interesting term, which is N grad C. And now this is motivated by the ion convection model of Konstantin and the Ignatova and Lee. So basically the motivation is the following. You put the cell into the fluid, and now basically the chemical attraction is like a force acting on the cells, but then basically the first model tells you that the cells are essentially moving at constant speed. So you have a force and now it moves at constant speed. It means that there are some friction exerted on the cells by the fluid. So basically there's a reaction force on the fluid. So this is the term that's coming from that. And now basically, if you introduce this friction force, and now everything becomes nicer. So previously, if you have buoyancy force and then you lose all sorts of energy dissipation properties. But then if you just look at this model, and now you can recover this energy dissipation. So basically, on energy perspective, and this is very nice, okay? And now you can easily check that the energy, free energy here is decaying in time. So if you have a decaying free energy, you can basically run all the machinery of Keller-Siegel equation together with Navier-Stokes equation, and now you can easily derive the following result, which is saying that if your basically it's like the previous classical result. If your total population is less than A pi, then you have global existence of solutions. But then we are not able to show that the solution is uniformly bounded in time on R2 due to some second moment issues. But then basically you have a solution. Everything are nice. And now actually this A pi threshold is actually sharp. If you are at A pi and now there's a group Lai Chen Chi and then Wei Juncheng and then Zhou Yifu show that actually you have global well-posedness. But then if your mass is bigger than A pi, you can easily cook up blow-up solutions for this kind of model. Okay, so basically we have a player here. My main problem to address is like, how do we understand this supercritical regime? Okay, so I'm saying that, okay, you can create a blow-up solutions, but then what happened for other data? There's no guarantee that, okay, for other case, they all blow up. Okay, so that's the main question here. So are there any question for the main theorem here? So basically, less than A pi, it behaves like the classical setting. Everything is very nice. And now above A pi, everything, yeah, it's very uncertain. Okay, so here, okay. So basically, we want to address the following problem. So we take a look at this coupled equation. We introduce certain parameters to highlight the relevant impact of different components. Okay, so again, we have this Keller-Segal equation with advection. And now you have a Navier-Stokes equation with this friction. And now basically this kappa will be chosen to be small, highlighting that the fluid effect is stronger than the nonlinear effect. And now the diffusion effect in the system. Okay, so that's assumption number one. And now new here will be viscosity. And now that will be also chosen to be small. Basically, it's like the Euler flow here. And now we want to find globally smooth solution with arbitrary large mass. So basically in 2 dimensions, you can do this, okay? And now, but then we also have some basic motivation of why we expect such kind of result to be true, okay? So the motivation comes from the serious work by experts here. So basically, let's focus on the first equation. Okay, let's focus on the first equation and then just ignore the Navier-Stokes for a moment. That's a little bit complicated. And now if you have this equation, okay, and now kappa here will be chosen small to emphasize that the flow effect is strong, okay? And now it's well established that if your U is suitably chosen, and now the potential singularity in this equation can be suppressed. And now basically this kind of velocity field is like what you learn in this in Anna's lecture notes and then later. So you can choose it to be exponentially mixing flows or shear flows, etc. Many things. But then the idea is similar. So basically you have you look at this equation. Okay, for arbitrary nonlinearity, you put it here. And now kappa is small. These two effects is smaller than the fluid effect. And now in Christian's talk, and then basically show you that if your vector field is exponentially mixing, and now you can do a page argument to show that the convection can enhance the diffusion here. Okay, so that's what we learned from previous lectures. And now I'm going to rigorously rederive all these things. Okay, so once you enhance the diffusion, and now there's a hope to use the diffusion to dominate the nonlinearity. As I mentioned, this kind of experiment is like a balancing between two forces. One is aggregation, one is diffusion. So if one of the player becomes stronger, and now it will dominate. So in this case, diffusion is helping you. So if diffusion becomes stronger, it will annihilate all the nonlinearities. Okay. Here. So basically, we'll treat this as our roadmap. So we are first going to introduce some enhanced dissipation of a very special family of flows. And now I'm going to use that to control nonlinearities, okay? So, but then it will be good to mention a little bit about what kind of flow we are using and now what kind of mechanism are we looking for here, okay? So first of all, the flow will be the shear flow. Now, in particular, for all this talk, I'm going to just use the wet flow. Okay? It's called the wet flow. Now, it is the simplest shear flow that you can, non-trivial shear flow that you can imagine. And now, what is the mechanism that we want to use? Okay, how do we dominate? Okay, so basically, we look at this picture. So we know that have a single equation have two different phases. So first phase, if you have in 2 dimensions, okay, if your data is bad and now you have a finite time flow up, and now if your data is in 1 dimension, and now your solution is globally regular in time. So basically, want to find a way the following. So originally, your data is like a 2-dimensional object, it's like a Gaussian. And now you somehow want to find a way to homogenize that in 1 dimension. For example, this is like a T2 framework. Originally it's 2D, but then you can find a mechanism such that it compresses 1 dimension. Okay, so basically this is like a function which is depend only on y. Originally, it is a function depends on x only. So that's the goal that we want to achieve. So is this clear here? So basically, 2D equations are hard, 1D equations are easy. I want to find a mechanism such that I effectively knock out 1 dimension in the system. Okay, so that's the plan. Okay, so now let's continue. So how do we achieve this? So it's very simple. So actually, okay, sorry, I forgot. There's a simulation done by Yao Yao and 3 undergrads in the IEU project. They do a simulation. So if you put a shear here, if the shear is not that strong, you form blow up. If the shear is very strong, you have spreading. And now the solution is completely regular. Okay, so that's the simulation. And now, basically, I'm going to dig into this realm of enhanced dissipation. Okay, and now try to achieve this goal of knockout 1 dimensions. Okay, so this is like a very simple effect. Okay, so let's just imagine, okay, originally we have a nonlinear equation, but then let's just throw out the nonlinearity, and now we have the passive scalar equation. We assume kappa is small to emphasize that the fluid effect is strong. Okay, so that's the assumption here. And now, basically, in the previous lecture, we already see that L2 norm is decaying here. Okay, the convection doesn't play any role. And now it will decay with a rate, which is kappa. Okay. And now kappa can be very small. So basically, it's like you have a cup of coffee, you throw the milk inside, you have to wait a minute for it to get homogenized, for the milk to get everywhere. Okay. So basically, the time scale here is the order kappa to the -1. Through our talk, and I'm going to refer this to the heat dissipation time scale. So this is the time scale on which the heat equations start to kick in. Okay, but then Michele and then Theodore do this nice simulation about doing a sine flow. And now if you do a sine flow, imagine this is coffee, this is milk, and now you turn on the sine flow, and now the milk will get homogeneous. So first you can see this filamentation effect. It creates some fine structure in the vertical direction. And now after a very short amount of time, and now everything gets homogenized in the horizontal direction. This is exactly what we are trying to achieve here. Okay, so basically this is the eyeball observation, and now it's very promising. So we are going to extract more about this structure. And now Okay, good. So to understand the idea behind that and then find the connection between mixing and enhanced dissipation, and now we just look at the following intuition. So small scale create fast decay. Okay, so you just take a look at the heat equation, and now you just do the undergraduate ODE, PDE class to do separation of variables. You can see that heat equation have two solutions. One is sine y, and now it decay with rate 1. So half-life is 1. And now if your solution is like a sine 10y, just create 10, jump here. And now the decay rate is 100. So after 1 over 100, the solution will decay very fast. So this is what we are looking for in this business. We are searching for small scale creations. Okay. So, and now, but then how do we achieve this here? Okay, so it's very easy. So basically imagine you have some milk here, and now you turn on the shear flow. Shear flow is exactly the one I write here, which is Y0. So it gets shearing. And now once this two endpoint touches the boundary of the torus, and now you're going to go back. And now you do basically after a finite time, and then you wind around T times. Okay, basically you can see you create some small scale in the vertical direction. Imagine you are starting from here, it's 0 when you walk up, and now you see some density, and now you see 0, and then you see 1, you see 0 again. So basically it's like the mixing scales here. Okay, and now this is what happens if you don't have any diffusion. And now if you have diffusion, and now the effective behavior is like you have a bump here. And now after a short amount of time, and now everything will get homogenized. And now that's exactly what we are looking for here. Okay, so that's the toolbox that I'm going to use later. Okay, so now let's continue here. And now, so we are going to do some analysis here, but then I'm going to make everything simple. So just focusing on this web flow business. And now, throughout the talk, I'm going to use this notation. So when I write bracket of that, means you take the average in the x direction. Now, when I write F0, it means you remove the x average. Okay, so basically, oh, sorry. Okay, basically, we expect that. Okay, after us, so what kind of function have 0 remainder? So basically, this kind of function will only depend on y. Okay, that, and now that's our end targets here. Okay, for this kind of homogenized solution. And now F0 equal will be identically 0. Okay, and now that's our end state of the system. Okay, so it's natural to just decompose the solution into two parts. One is the x average, one is the remainder. Okay, so just from this observation in our daily life, and now we know that the remainder will decay very fast. In fact, like 100 years ago, and now Lord Kelvin already showed that the L2 norm of the remainder will decay with rate kappa to the third. Okay, so in this business, we care about this power here. Okay, basically, all the constants are not that important. We only care about the power. And now if that power is less than 1, we say that there's an enhanced dissipation. So why that's the case? So you can take a look at this expression, and now you can see that the L2 norm will decay to half of its original value within time kappa to the -1. Okay, so recall that the heat dissipation time scale is kappa to the -1, so it's long. But then when you have kappa to the -1/3, and then it can be very small when kappa is small compared. Okay, so suppose you take kappa to be 1000, and now this kappa to the -1/3 is like 1/10. Okay, something like that. Okay, so basically this is the enhanced dissipation effect that we are looking for. And now in the latter analysis, I'm going to need a rigorous derivation of this result. So it's very easy to do. So, but then the idea is important, okay? So first of all, according to Lord Kelvin, let's do a change of variable here. So capital X is X minus YT. Basically, it's the flow map of this quad flow. So basically, you move to the original, back to label map. Okay, so X minus YT. And now capital Y is Y. Okay, and now, okay, here I will need to write down this notation because later we are going to use it many times. Capital X is equal to X minus TY. Capital Y is our original Y. And now our passive scalar equation become this equation. Okay. And now later, we can see that in this new coordinate system, this whole expression, even though it looks nasty, but then it basically incorporates the advection and diffusion at the same time. So it's very nice. And now it played a role of Laplacian. So basically later, we're going to see this expression a lot, but please don't get scared. And now this is nothing but the Laplacian, okay? And now, here, you can easily do a Fourier transform. So this Fourier transform of this operator become minus kappa k square plus eta minus kt square. And now you can easily solve this equation using characteristics. Okay, so you can just directly write it out. And now basically you have a tau minus eta over k square here. And now you expect that when I integrate in time, I integrate tau, and now you gain another power. So at the end of the day, you can easily get this kind of decay, okay? And now here, the import, I will further rewrite it like in this fashion, okay? So you can see that in this expression, if t is of order kappa to the minus a third, this factor will be significant. So your solution will decay to a half within time kappa to the minus a third. Okay, so it's very easy to see. And now basically this is very easy to do. Okay, and now it is done by Lord Kelvin 100 years ago. And now this is in his original paper. And now he said arbitrary function x minus yt. And now you can solve this t out. And now you can see this interesting little mu t cube here. Okay, m square, beta square, I just assume that to be 1. And now that's what he observed. Okay, but then there are many recent development in this business. Okay, so basically people care about other kind of shear flows. Okay, not just the quad flow. Quad flow, you can do everything, but then for other kind of shear flows, it's relatively hard. And now basically, Jacob-Joseph, Michele-Cucuzzi use this hypercoercivity method we've just learned this morning to derive enhanced dissipation of shear flows. But then I'm not going to dig into details. And now there are many results related to that. And now recently there are many works on using stochastic method to derive enhanced dissipation. And now, I'm not able to saturate all the results here. And now basically, Sam and Theodore do many works, and then recently Elgin Lees and Martin Lee proved the exponentially mixing of alternating shear, and now you can upgrade that to enhanced dissipation, okay, using machineries in machineries here, okay. And now also do a related work for bi-Laplacian flows, and now basically you can use enhanced dissipation subject to bi-Laplacian to suppress blow up in Kuromoto-Shivashinsky equations. And now basically there are many other works. And now, okay, so that's on the just advection diffusion equation level. But then when you understand this kind of phenomena, okay, there's a broader playground that you can use this kind of mechanism. So first of all, you can study shear flow stabilities. Okay, that's our topic later. And now you can also study plasma physics, especially when you are talking about Fokker-Planck equations and Vlasov-Poisson equations, and now this play major roles. And now Roman Shvitikoy also finds some interesting application in collective behaviors. And now 2 months ago, Gautam wrote a paper on using this enhanced dissipation to speed up sampling of Langevin dynamics. Okay, so it's, yeah, you have some potential here to use it in sampling theory. Okay, and now basically we have an idea. So I'm going to give you a sketch about how do we actually apply this machinery in a nonlinear equation. Okay, so just focusing on a simple model, which is called the advective, okay, modified Palakkala-Segal equation. And now we have the advection, we have the diffusion, and now we know almost everything about this equation. Basically, solving by characteristic, you know everything. But then you put another decoration here. And now this can be modeled by many different aspects, okay, chemical reaction, etc., chemotaxis, all the things that you can imagine. But then we want to derive this picture, just visualize this picture. So originally the problem is two-dimensional, and now, so it's hard. So instead, we're going to decompose the solution into the x-average part and now the remainder part. For the remainder part, you expect it to be decaying very fast, and now it doesn't matter. For the x-average part is the main remaining feature of the solution here. Okay, so we just take the x-average and now take the remainder. Okay, you have two naive-looking equations. And now, what is the observation here? So the x-average means that you average out the x variable, x become dummy, and now basically it's a one-dimensional Palakkala-Segal equation. And now we know that one-dimensional equations are very easy to handle, and now it's very nice. So we expect this kind of solution. The first equation is well behaved under the assumption that this remainder part is very small or decaying very fast. Okay, so this is the first observation in this scheme. And now the second observation in this scheme is that, okay, we can extract some nonlinear enhanced dissipation from the remainder. Okay, the idea to do that is fairly simple. So just like many works, okay, basically, if you want to derive enhanced dissipation, you can compare the passive scalar solution to the inviscid problem. And now here you choose to compare it to a different one. So I have a nonlinear problem, but then I already know everything about the passive scalar equation. Let's just compare this eta naught and now n naught. Okay, so basically this one I know everything. Within kappa to the minus a third time, everything decays to almost nothing. So a fourth. And now we just need to show that on this relatively small time scale, this n naught is close to eta naught. And now this can be achieved through energy estimates. Okay, so you just take a derivative of this difference, and now you have this nonlinear term. And now you can see, you can do an integration by part here. And now you can absorb this term into the diffusion. And then the remaining part, you do some classical energy estimate you can handle. But then the key observation is that I'm only care about a very short time, kappa to the minus a third. So this coefficient really helps me. So kappa times kappa to the minus a third is still fairly small. So this is perturbative. So if you just drop this term, this is decaying. So this deviation is very small on a time scale, on this 0 to kappa to the minus a third time scale. And now you can say, oh, they are close. Okay, so now you can do the nonlinear enhanced dissipation. You just add these two up. At the time kappa to the minus a third, you add these two up, and now you get a half. So basically, your nonlinear solution will decay to half of its original value within time kappa to the minus a third, and now that's the enhanced dissipation, nonlinear enhanced dissipation. And now we rigorously justify that n not equal is fast decaying and hence perturbative. And now our previous assumption, our previous claim that the end bracket is smooth can be justified. Okay, so that's how you run this whole argument in this simple model. So everything can be very simple here if you just consider the Keller-Segal equation, classical one. Okay. And now basically by extending this result, you can get the suppressional blow up on torus T cross R. And now by further extending this result, you can do it for R times T. Okay. But for R times T is a completely different story because the mixing there is extremely slow. Okay. But then you can use what's called the quenching effect of the shear flow and now do similar schemes. And now you can suppress the blow up. Okay. So basically, that's the plan we have for a simple model. And now I want to move a step forward and now address the coupled equation. So any questions so far? Very good. Okay. So let's continue here. Okay. So we take a look at this original equation. Okay. We have kappa and now it is small. Okay. Emphasizing the effect of the fluid. And now you have the Navier-Stokes equation. And now we want to try to find the global smooth data. Okay. There's a recent development in this story. So basically, if you just replace the Navier-Stokes equation by inviscid porous media equation, okay, and now for arbitrary data, you don't have any blow up. So on a channel, okay, so that they can rigorously prove that. And now the idea there is like you want to extract some softer version of this homogenization effect here. And now you can somehow close the estimate. Okay, so that's the remarkable result. And now we will continue here. So basically, now we are dealing with a system. Okay, so I'm going to linearize. So that's the standard story here. I want to use the Couette flow, but then the Couette flow might not be stable under this perturbation. So I'm going to linearize around the Couette flow, okay? Not linearize, you write it in a linearized form, okay? So you have a passive scalar piece, and now you have some error terms, okay? Basically, these error terms can be large, and now you want to control them, okay? So the main idea is similar to what we've done here, but then we have to do it in a more delicate fashion, okay? And now, basically, understanding this finding large data result is equivalent to studying the stability of the Navier-Stokes equation in 2 dimensions, okay? So you just think of this n, okay, this evolving n as a forcing on your Navier-Stokes equation. And now you try to show that this forcing doesn't matter that much, okay? And now, if you are talking about stability of fluid flow, and now there's a large literature on this. Now I will not dig into details. And now, basically, what we can show is that if your initial perturbation of vorticity is on the scale nu of half, and now your kappa is small compared to nu, and now you can show that there exists a globally regular solution for all time. And now you get all sorts of enhanced dissipation results for the remainder, okay? And now basically you get a sharp version here, okay? So that's the main result. And now here, I didn't put any constraint on the L1 norm of n. So basically the L1 norm can be as large as you want. And now basically, if you don't have any fluid flow, and our solution can blow up in finite time. But then thanks to this Couette flow mechanism, it can stabilize the dynamics here, okay? And now we are going to use similar, we are going to move a step forward and now do some further delicate estimates, okay? So here, because you are handling, basically because your flow is no longer stable, so I cannot directly do this simple comparison argument to make everything work. But we can build some interesting functionals to capture the behavior of the solution. So we are going to do the same thing as before. I'm going to move to a new coordinate system. And now our equation is just like a passive scalar part. plus some nonlinearities. I'm not even going to write down the details of this nonlinearity, but then they are enemies, okay? And now, in order to capture enhanced dissipation, you don't really need to do the explicit computation here. Basically, right now we give up all the hope of deriving explicit formulas for PDEs. And now, but then you can design some nicely chosen functionals to capture enhanced dissipation. One of the nice functional here is motivated by the previous studies. Okay, it's just arctangent, so it's very easy. So this kind of, you can consider an L2 norm with a weight. This weight is bounded. Okay, this weight, you can see arctangent is between -π/2 and π/2, so it's a bounded quantity. So these two are just nothing but an order 1 quantity. Okay, it will not hurt you. But then when you are, this is why it is called a ghost. You don't really see it in your energy estimate. But then my claim is that the Wi here captures the mixing effect, and now the We here captures the enhanced dissipation effect. Okay, I'm going to rigorously justify my claim in the next slides. So again, okay, I cannot do too much for the nonlinear problem. Let's focus on the passive scalar equation that I wrote down here. Again, this piece is the Laplacian in the original physical variable. And now you can do, okay, Fourier transform, get this equation. And now you just take a look at these two weights, and now you can take a time derivative. And now you can see one of the weight is like a 1 over Laplacian. Okay, so k squared, let's just drop that for now. And now this is like a 1 over Laplacian. The other weight, you have a interesting looking kappa to the third in front. Okay, so that's the property of these two weights. Okay, and now basically that summarizes our observation here. It's fairly simple. And now you can start to take time derivative. But then this time, because W is depends on the time. So you have an extra term here. These two terms are called Cauchy-Kovalevsky terms. And now basically, if you just plug in these two expressions inside, you can basically, when you are combining these two terms together, you have a nice term. Okay. When you look at this term, you have an expression like this. Okay. So basically for the first term, it tells you that the L2 norm is decaying with rate kappa to the 1/3, k to the 2/3. Very nice. Okay, so sharp enhanced dissipation rate. Moreover, you have a damping term here. And now because your solution is bounded, thanks to this expression, you automatically know that the H-1 is L2 integrable in time. So just by looking at this simple looking weight, okay? So that's the whole observation here. Basically, by looking at this functional, you automatically get enhanced dissipation and mixing. And now basically these two go hand in hand. Okay, so basically whenever you have mixing, you have enhanced dissipation. In this special case, if you have enhanced dissipation, you automatically get mixing. So these are it is discussed in a series work by Elgindi, Codizzolati, Matthias Delgadino, and Galton Iyer and Feng Yuanyuan. And the other way is done by Michele Codizzolati. Okay, so basically that's your helper. Okay, and now we look at the nonlinear problem. Okay, so you take the time derivative of this, and now you create two sorts of nonlinear terms. And now the first kind of nonlinear term have kappa in front. Okay, so basically you do same kind of estimate. And now you can see that the first kind of term have kappa in front. It can easily be controlled by kappa to the 1/3 enhanced dissipation term. So this term drops out. There's another kind of term which does not have any kappa, because when you are studying fluid equation, the fluid convection term will not help you. It's just like order 1 quantity. In order to control that, you need to use this mixing estimate. Okay, in this model, mixing norm actually have a very concrete physical interpretation. It is just like the chemical gradient here, because the Laplace C equals to n, so the chemical gradient is exactly the H-1 norm. So mixing and enhanced dissipation come together, help you to control all the nonlinearities here. And now once you control all of them, you are done. Okay, so basically that's how you prove this kind of result. Okay, and now basically my time set is up, and now I'm going to have some general questions like I want to improve the stability threshold, and I'll discuss the problem in 3 dimensions, and now consider the fully parabolic case. So for the fully parabolic case, it's hard. So basically, if you just look at the passive, you just look at this Keller-Segal equation with chemical convection. Basically, it rules out most of the exponentially mixing flow that you can use, because you can see if you have exponentially mixing flow, chemical gradient can grow exponentially, and now your nonlinearity can also grow exponentially. And now if that grows exponentially, you cannot control. So basically, you can do for shear flow, and now you have to put some assumption on the initial data for the remainder. And now we are trying to improve on this threshold and then try to get rid of this A dependence here. Okay, so that's all for today. Thank you.